All right, let's get started here. Oh, it's warm. Okay, so you can't see any of this. Now you can. Okay, so we had the celebration on Monday. Hopefully, did some skimming. There are some students didn't do so hard on the last part of it, right? We've been building on that a lot, so that's a little bit worrisome to me. Um, Remember, right, that we're rapidly running out of times for you to like improve your grade. A couple of you've gotten F's on both celebrations, right? If that's you, like you need to rapidly learn everything, right? And you should be coming to me like you should be getting extra help for several hours a week and like working on it's gonna if that's you to pass this class to get anything that's close to acceptable grade, it has to be the top priority of what you're working on, right? Um, you have all the resources, right? Remember that you guys can watch the videos of any lecture that I give, right? By going to the Zoom tab, right? Clicking the link for cloud recordings, then clicking on the recording of the appropriate day. The password will automatically be pasted, right? Into your, so you just control V and it will be there, all right? So do that. I don't know. I'm just worried where some students are and that they're not coming to get extra help. Uh, Especially on the normal distribution stuff. Because remember, everything we did last week built on that, and everything we're going to do today will build on what we did before, right? So, yeah, just right. A handful of students who I thought might drop the course on Monday didn't, right? So don't say I didn't warn you, right? And don't say that it's going to take a lot if you have been getting, if you've got F's on both celebrations so far. Okay, so the first section we're going to do today is on the basis of hypothesis testing. In A2, we'll be testing a claim about a proportion. We probably won't finish that second section, but we'll do as much of it as we can, all right? And it's important that you guys pay attention. In my other section today, I had some students who didn't seem to be all there, and that, again, was worrying to me, right? I know it's hard to focus for this long, right? I have trouble myself, but doing what you can to stay focused, right, is important. And feel free to ask questions, right? That's something that would be good for everybody to do. Okay, so we're going to kind of give you the basics of hypothesis testing. Some of the stuff is going to be confusing in isolation. There's going to be a little bit maybe more text today, so please, don't you remember you get all these PowerPoints online, so don't write more than you need to. So we're going to do, these are kind of like the subparts of a hypothesis testing, right? The null and alternative hypothesis, calculate the test statistic, conclude if the hypothesis should be rejected or accepted, and then actually state that hypothesis, the rejection or the hypothesis in everyday language that nonetheless is accurate, right? So here's kind of the main idea underlying hypothesis testing, right? We mentioned this earlier, right? Let's say I have what I suppose to be a fair coin, right? But I flip it 30 times, all 30 times it comes up heads. The conclusion would be that what? It's probably not fair, right? That something is loaded. So, but the reason why you would say that is the chance that a coin would come up heads 30 times in a row is very low, right? But it is theoretically possible that that could happen, right? It would just be very unlikely. So you assume something in particular, right? And then you find out, right? So we assume, right, in this class that, let's say, something that you've been told, right? Something that's published. The average weight of a dog is, I don't know, 50 pounds. I have no idea if that's anywhere right? The mean weight, right? Then you collect a sample. Say you got 30 dogs. Their mean weight is 30, and you're like, ooh, I think their mean weight is 45 pounds. You say, I really think the mean weight of dogs is less than 50, right? So basically what you have to do is you have to find out the probability. Hey, I think it's less than 50, right? What's the probability if, so assume that you're wrong. Assume that it is 50. What's the probability then that a randomly selected sample has all dogs that has a mean of weight that's 45? If that number is 20%, you mean like, no, that's not really evidence against it, right? Because there's a 20% chance that that would happen by chance, right? If that probability is 1 in 10,000, if it's the probability of having that low of an average is 1 in 10,000, you're going to reject the initial assumption, right? And say, actually, it's less, right? So that's the main idea. If you didn't follow all that yet, that's okay, right? Because I'm going to teach you each of the elements. So one thing, right, that you have to notice is a hypothesis in statistics is always a claim about the population. It's never going to be a claim about the sample, because the sample you have access to, right? The person who's doing the study, right, collected all the data about everybody in the sample. So there's no point to hypothesize about what the mean of the sample is. Just calculate it. Just calculate the standard deviation, whatever it might be, right? This first one's a little bit confusing, but it is a hypothesis, right? And they're usually some sort of statement, right? So this one says, and they usually reject conventional wisdom, right? So this is, scientists, researchers claim that the mean boiling point of water is actually some temperature other than 100 degrees Celsius. So you could write that in symbolic form as mu is not equal to 100, right? You're never about a sample, right? You done? Okay. See if you can write that one symbolically and read the rest of this one. Okay. So thank you. Now let me get your note sheet as well. What? Okay, well, you had 2 hours though, right? Which is the amount of time that I scheduled students for. Okay, well, then just clear your calculator memory. I'm willing to let you take more time if you want, but then you'll have to work that out with wherever you need to be, okay? Second, plus sign, 7. Yeah, yep. 2, yep, 2. Okay, thank you. All right, I'm gonna keep your note sheet and then I'll pass them back once everything gets back to students. Okay, never mind then, you're good. So hopefully you wrote this down, right? Mu is less than 5 for this one. Not too difficult, right? So you want to see basically, right, with reasoning and statistics, right, you want to see, is something, right, if holding a particular assumption, right, something that, so I hold some assumption, right, but then I observe something that's unlikely, or in some cases, very unlikely to occur given that assumption, right? Just like the example I said, right? The assumption that you don't know anything about a coin, hey, it's just your average everyday quarter, right? 50% heads, 50% tails. You flip it 30 times, you get way too many heads, say all 30, 29, 28, 27, right? That's something that would be extremely unlikely to happen by chance. Therefore, you reject the initial assumption that P was equal to 50. You see what I'm saying, right? So that's the whole idea with hypothesis testing. But to get there, you need to format it, right? So these are your hypotheses, right? But as a convenience mathematically, often the way that you write your hypothesis is not what you actually think, right? So you want to do a formal hypothesis, right? So the formal hypothesis test is you have 2 hypotheses. One is called the null, which sounds like 0, right? So one way you can think about it is that there is no effect, right? I did something, right? I think drinking energy drinks before a track and field competition will make me do a longer long jump. So my assumption, right, the null hypothesis would be that the mean long jump distance is the same of whatever I thought it was before, right? So your statement of your null hypothesis will always be something like your mean equals 30, your standard deviation equals 800, your proportion, that's a common one, equals 1%, something like that, right? Will it ever be something like this? P hat equals 0.1 or X bar equals 50. What do we think, class? No, because these are about the sample, right? And you have access to the sample. Why hypothesize, right? Why would I hypothesize about the percentage of students in this class that own a red car? I can just ask y'all, right? Why would I hypothesize about the standard deviation of y'all's weights? I could just weigh each of you and calculate a standard deviation, right? Not necessary for sample. It's always for a population, right? So this will be your null hypothesis, right? And a lot of times this is conventional wisdom, right? So it's kind of, we're calling it your first hypothesis, right? Because if you truly believe this, you probably wouldn't need to take a study, right? I mean, sometimes it's good to confirm known fact with a study, right? But you don't confirm a study, you don't really do a study to confirm water is wet, right? If you wanted to show that water is dry, you would need to conduct a study. So typically what you actually believe is your alternate hypothesis, which will always contradict the null hypothesis, right? So if the conventional wisdom is the mean is equal to 30, perhaps the null hypothesis would be that the mean is not 30, that the mean's over 30, or the mean's under 30, depending on what is believed by the individual, right? It will always be one of these three things. So to reject conventional wisdom, you want overwhelming evidence, right? Or at least very strong evidence. So because we require strong evidence to reject a null hypothesis, you can reject a null hypothesis, right? It's not perfect. It doesn't mean that you're sure the alternative hypothesis is true, but you say you reject it. You don't say like, I accept the null hypothesis. You say, I fail to reject it, right? Because that's the default position, right? You might even have evidence supporting the opposite way, right? But it's not strong enough to reject, right? So since you default to your null hypothesis, right? You never say that I'm accepting or proving my null hypothesis. You only fail to reject that it's false, which is okay because you really believe the alternative hypothesis most of the time. Again, that won't make a ton of sense without a lot of okay, without an example. So let's do some examples, right? So this sounds like a lot. I don't know too many. My parents used to watch golf on TV. I found it very boring when I was a kid, but now they're not really, they don't follow golf anymore. They haven't since they were like my age, a little bit older. All right, so this sounds too high to me, right? So if it was me, my alternative hypothesis would be that it's less than 70, but that's not what they're saying. They're saying that it's not 70, right? Now, first you want to think about what sort of parameter is this a hypothesis about? Is this a hypothesis? And it's usually going to be these three things, typically. Or four, I guess. Variance, standard deviation, proportion, or mean. Which one is this about? Proportion, right? And are we talking about P or P hat here? P, right? It's always about a population parameter. So the null hypothesis is always that it's equal to something. So in this case, the null hypothesis, right? You could write it in words too, right? But I'll say it in words, but I'll write it down in symbols. The null hypothesis is that the proportion is 70%. But you'd want to write that as a decimal, so 0.7. So the null hypothesis is the proportion of men who watch golf on TV is 70%, right? And you can see that that's the null hypothesis because that's the conventional wisdom, because that's claimed by some advertising corporation. But you don't really think that. You think these people say this, but I think that that's BS, right? What you really think is typically your alternative hypothesis. So in this case, the alternative hypothesis is that it's not equal to, right? Because this person does not have a thought about whether it's less than or more than. So right, you might notice here, so you could say this is typically the case. It's not always the case, but almost always, right? Notice the original claim is the same thing as the null hypothesis, right? Sorry, not the null hypothesis, the alternative hypothesis, right? I'm going to take attendance. Try writing this next one out on your own, right? And check with your partner. This is not, trust me, it'll get harder than this, right? You can write it down in symbols, but maybe try to say it in words. All right. So the way it's written is not as much as like an actual study. So the null hypothesis here, did anyone get population standard deviation is equal to 4,000? Because it's always an equal to statement, right? Even though here that's for some reason believed that it's greater. So in this case, it's a little bit different, right? Because that's all that's written here. Perhaps you believe it and it's not even, conventional wisdom that it's equal to 4,000. But if you want to test this hypothesis, right, you just kind of pretend that the conventional wisdom is that it's equal to 4,000. Because that's a good way, right? If you can show that the conventional wisdom, right, the way that you can show that it's definitely more than 4,000, or as definitely as you can, is to assume that it's 4,000 and show that certain things that happen are unlikely to happen if it's that small, right? Does that kind of make sense? Okay, so let's actually think about this. Let's think about the top example, right? Can anyone describe, let's say you wanted to test this, right? You wanted to actually get evidence that supported either the null hypothesis or the alternative hypothesis. What might you do? Yeah. A survey, right? So you would want to look at in that survey, right, whether it is how many do in your survey, right? If it's right, so you want to get right. So when you're collecting a survey, right, what you're really doing is you are getting at least one sample proportion, right? So you would find p hat, right? Now suppose p hat was 0.3, you would say, yeah, right, that's wrong. Now, assuming your sample is correct, done simple randomly. Now, if p was 0.65, you would say, I'm not so sure, right? It's close to 70, but it's not 70, right? Maybe the real mean is 68 or 64, right? So the question is, how different is different enough, right? So to do that, you need to look at the statistics, right? And you can think of a couple of things, right? If I collected a sample with 20 people, well, let's say it seems small. Let's say, well, you can't, this doesn't work out as a percentage of 20 people. Just imagine, no, yeah, it does. All right, I do a sample with 20 people, right? And it gets 65%. And you're like, no, I don't know. Now, if it's 20,000 people, then that's bigger evidence, right? So you need to have a statistic, right, that calculates that, right? If the standard deviation is small, that also means, right, a change is more significant, right? Because it's more a change in more terms of more standard deviations. So let's look at the different So you need a number that kind of cuts through all of that tells you how much, right? How different is different enough, right? That is what the statistic does, right? So one thing I think about this is how different is different enough. And when I think about that, I want to think about part of that is your taste, and we'll go over that, right? But part of it's how sure you want to be, right? Would you rather go with the conventional wisdom incorrectly, right? Or rather reject it, right, when you shouldn't have, right? So it depends on how significant of, like, how far away do you want it to be? But the way to do that is to calculate these things. So with a proportion, it's good to remember what this is, right? So notice your top is your difference between your p hat and your p, right? So that says how different is my sample than what I have been told the population is, right? But that's just but that in itself is not enough because that depends on how spread out the sample is and how big the sample is. So this right here, does anyone recognize that formula? It was written on your note cards, any of your note cards on Monday. P times Q over N. Well, hint, you're calculating a z-score, which means you're dividing by a, this is the standard deviation, right, of a binomial sample of size n, right? So it's the sampling standard deviation, right? So roughly this is saying this should help us factor everything that's into this, right? Right? If I find a z-score, right, I know a z-score of like 3, that's really far away. A z-score of a half, not as big of a deal, right? Notice these also divide by standard deviation. It's just the standard deviation scaled, right? You did this in the last page of the celebration, right? Scaled for a sampling distribution, right? As opposed to just 1. Now, this again goes to chapter 7. What's the difference between these two formulas here for Z and T? Just have to look at it and tell me. What? Well, what do you mean by that? Like we're finding how far a sample mean is away, but yeah. Yes. So, but we actually have them in both, but it's the type of standard deviation. So notice for Z, this is sigma, which is the standard deviation of the, and then this one is the standard deviation of the sample, right? Because, right, now, which one would you rather have? Population, right? So this is the better one to use, right? So if you have the standard deviation of your population, use this one. If you don't, use T, right? And I told you, right, there's 2 ways to calculate, right? This is very similar to what we did in the last section, right? We create a confidence interval, right? A confidence interval is very similar, right? Here you just have a test you want to see is basically what you're doing in hypothesis testing is seeing if your value's in your confidence interval, right? Now, here's why. So population standard deviation is better, right? Now, if I don't have that, a good estimate, an estimator for my population standard deviation can be your sample standard deviation, right? Because I don't have it, right? Just like you could say, hey, my point estimator for P is P hat, right? Same idea here, except remember that S is a bias estimator of. So that means that using that estimator introduces a larger margin of error. So you have to use the t distribution if you do not know the standard deviation, right, of the population, right? This t distribution will have thicker tails, right? And that makes sense because, right, since the way I think about it, this may not be the best, is that since I don't really know what sigma is, I'm just guessing that it's S, there's more uncertainty. I'm more likely to get something that's farther out from the mean because maybe the sigma is bigger than I think it is, right? So that's why you have to use the t distribution. Now, which one do you think you're going to use more often in the mean case? Well, let's think about this. This thing is to I am doing this to try to make it, because I have a hypothesis about the what of a population on the right side of this slide. I have an hypothesis about the population mean, right? Which means I don't know the population mean for certain, right? If I don't know the population mean for certain, am I likely to know the population standard deviation for certain? No, right? So I'm most likely, right, in the mean case, this is going to be most of the time, right? But today, since it's easier, right, with proportion, right, there's just one formula. It's easier to use, basically because in a binomial, right, P determines the standard deviation. That's a little bit easier to do. So that's the one that we'll focus on the second half of today's lesson. So let's calculate a test statistic. So the claim, right, so let's put some of the information in here, right? So the claim is that the proportion of peas with yellow pods is equal to 25%. That sounds like a genetic thing, right? I've bought, beans, right? You get beans, they're mostly green, but every so often there's like a yellow one in there. Anyone who's bought green beans at the supermarket sees that, right? So if you are breeding, say, two plants, right, each of which has one recessive yellow gene, it needs both of them, right, to get it. So half the time we'll get it from mom, half the time we'll get it from dad. I don't know if plants have mom and dad, right, but just roll with it, right? So 25% they'll get it from each, right? That's the accepted way of understanding it, right? So to see that, right, we collect a sample of 580, but we get some other number, right? So the question is, that's different than 25. Is it very different than 25? Doesn't seem like it, right? But that sample is hella big, right? So maybe that is a significant difference. So let's figure that out. So of the formulas that are written here, which would be the appropriate one to use? Left, middle, or right? Left, because we're talking about a proportion. Okay, so let's write that down. So that's the formula. We have to identify the things here. Okay, so let's look at the first thing in the formula. What is p hat? Is it the 25 or the 26? Yeah, but I want to write it as a decimal, right? Which means that p is 5. Now, you want to be careful about this. This p is not what, we don't know p for a fact, right? We only know p naught for a fact. So with the null hypothesis, I'm assuming, right? Well, we don't have the whole thing, but you would be assuming that it's 25, right? And you're seeing how different is 26 than 25 with respect to what we know about the sample, right? So then we just need to enter in the rest of the information. N in this case would be what? That one's easy. 580, right? The bigger the sample, right, the more significant small differences in proportion would be, right? And of course, Q is just 0.75, because remember, Q is equal to 1 minus P, right? If you don't like remembering Q, you can just write down 1 minus P every time, but then you have to do parentheses and stuff, right? So let's plug this in. If you're doing this in your calculator, I recommend doing it in one line, but be careful how you arrange this, right? Because notice this is technically a complex fraction. It's got division inside of a division sign. All right, now notice this top, right? If I subtract the top, I get 0.012 or 1.2%. That's the differences in the percentage, right? But you don't know, right, whether that's an important difference in percentage or not without taking into account the sample size and the standard deviation of the sample. That's what dividing by this does, right? So at the end, you get a z-score of 0.667. That tells you how far away, right? So the fact that's positive means that I have basically I'm 2/3 of a standard. I have 2/3 of a standard deviation more yellow peas than I would expect to get, right? So that can help me find the probability of having a number this high, right? Since you can't find out the probability of, right, this is, remember, right, this is a continuous distribution. So the probability that you have any percentage, right, exact percentage is 0, roughly, right? Or infinitely small. So we really want to end up turning this into a probability that I have something that's 26.2 or more, or as extreme as 22.6 in the case of a two-tail distribution, two-tail test. Don't worry that that's overwhelming, right? Just try to focus on how we do each part, and I promise we'll get them all together, right? This calculation isn't too different than calculations you've done before, right? So are we good with this? Okay, so let's talk about the critical region, right? So the critical region is the set of all values of the test statistic that causes to reject the null hypothesis, right? So it's for either Z or T, right? Depending on it, right? And that depends how sure you want to be, right? So the Z, right, is going to depend on a couple of different, things, right? But roughly it's going to depend on your significance level, right? So Z is how far, right? So let's say the critical value of Z was 0.6. Well, this is more than that, right? So it's more extreme than our critical value. So now it's in the extreme region. So that means we would reject our null hypothesis, right? If the Z statistic were 0.8, we would not reject it, right? Because it's within the range of what we consider normal. So the significance level is the probability that the test statistic will fall inside of the critical region, right? So here might be your critical value, right? That's a Z value. And then this right here is going to be your alpha level, right? If you just have one event, it's not that unlikely, right? So you choose this, but you can see the overwhelming things, right? Basically, right, and we'll talk about this more. Alpha is how likely your event is to occur by chance, right? So suppose right? So if you choose an alpha of 1, right, that means I want to stick with my null hypothesis unless I get a value that's so extreme. The probability of getting a value that extreme or more extreme is 1%, right? You can see an advantage to that. Then you're pretty sure if I reject the null hypothesis that I'm not doing so willy-nilly, right? That I'm not just saying, hey, I thought the average was 25 and it ended up being 26, so I'm going to reject the null hypothesis. No, don't do that, right? It could easily be 26. So here, right, the significance level. Now, if I choose a significance level of 5, that's what I'm saying is I'm okay with rejecting the null hypothesis 5% of the time I'm doing it wrong, right? Or 10%, right? You choose that based on how important it is, right? The higher you make alpha, the more likely you are to make a different type of mistake, right? That you don't reject the null hypothesis when you should have. So typically we choose small numbers for sigma because, right, if we're going to err on the side of anything, it's going to be on the side of the conventional wisdom, right, which is what your null hypothesis is typically. Questions? Again, it's easier to see this when you have an example, right? So depending on your critical values, right, you might want to have a two-tail or a one-tail test, right? So we have two tails on the left, one tail on the right, but then if you're doing one tail, right, of your normal distribution or your t-distribution, because they're symmetric, the question is which tail, right? So let's draw what each of these looks like. So when you have an alternative hypothesis, right, that is not equal, you use a two-tailed test. So here's my distribution, right? I've chosen my significance level. I want to find the critical values that cut off alpha over 2 on both ends, right? This makes sense for the not equals, right? Think about the test where I said I thought the proportion of men or whatever adult men who watch golf was 70%, right? If I find out that if I get a sample that 95% of men watch golf or 10%, both are extreme, right? And both would support rejecting that hypothesis, right? Now, if I said, hey, my actual alternative hypothesis is less than 70% of men watch golf, right? Having much more than 70% would not support rejecting my null hypothesis, right? Does everyone see what I'm saying? Right? My alternative hypothesis is less than 70%. Or yeah, then something like 90% does not support it, right? Even though it's way more than 70. So in this case, I only want to look for, right, if I'm looking at less than, extreme on this case, but I want my area to be alpha. So the entire area is alpha and it's on the left. Likewise, if I thought much more than 70% of men watch golf on television, which is definitely not true, maybe white men, conservative men over the age of 60, maybe, but you know, don't have anything better to do, right? So this is using the critical value method, right? The P method just means like I have my test statistic. If I'm doing a right tail test, I would really like to know what's the area to the right of Z, right? Or if I'm saying I think it's less than, right, I would really like to know what's to the left of Z. And if I don't have I just have a feeling that the number is wrong. I don't know how often that happens, right? If someone says, maybe unless you just have a friend who's known for making crap up, right? But you don't know anything about it, right? I just assume it's wrong because, you know, Bob said it and Bob is just generally full of shit, right? But if it's normally you have a thought about, right, hey, I tell you, you know, 80% of men, 80% of, you know, college-age men in Illinois visited France last year, you would say, I don't believe that. That's way too high, right? Or you would say, if I say, hey, 1% of Illinoisans visited another state, you would say that's way too low. Rarely you would say, I know that that's not right, but I'm not sure if it's too low or too high. So the two-tailed test is the least commonly used one. So you kind of get what I'm saying, right? If you have an alternative hypothesis, you generally have an idea of which way that hypothesis should be. But in the two-tailed test, you're going to actually have two critical values. But the nice part is, since it's symmetric, they're going to be negative and positive of each other. So in all of these cases, P is equal to the area that we have. Questions? I know this is a lot of information, right? Just try to write this down, try to store as much of it in your brain as you can, then try to recall it when I actually go through an example. So let's take our 5-minute break now, all right? And then if you really want to, you can try this, right? I will go over it though. All right, let's come back together. So this first one, I read the left-tailed test, right? That means I think my value is less than something, right? So I want to find the p-value, right? So let's draw this. So my z is negative, which means it's to the left of center, right? And then I'm looking at a z-tail test, right? So we can use our z chart, right? That's why I had y'all have that out, to find out the probability that you're in this area, right? Notice the chart does represent area from the left, so no significant thing needs to be done. You go to the appropriate part, and then you can highlight your value, and there it is. I want to be careful here. This p-value, it's confusing because p here means probability, right? The other one is proportion, right? So this is the probability that you would have a z statistic of that. So I might make that uppercase p, right? So p equals that number we just found, 0.0472, or roughly, right? So roughly 4.7% of that area is in here, right? So suppose you were doing a hypothesis test, right? And you got something like this, and you're doing a left-tailed test. You would say, hey, the probability my sample, I'll answer your question right after this, right? See if I did this correctly, right? The probability that my sample would be this small, right? The proportion would be this small, the mean would be this small, or smaller if my original null hypothesis is correct, is 4.7%, right? If you're saying my significance level is 5%, well, that's less likely than 5%, so then I would reject my null hypothesis. If I said I want more overwhelming evidence, I want to know that it's like less than a 1% chance of having by chance, right? I would not reject the null hypothesis, right? And we'll do examples like that. Ulysses, you had a question. Oh yeah, sorry about that. Thank you. Yeah, that makes a difference, right? So then it's not that close to 5%. So it's definitely, under 5%, right? But yeah, that's just my dyslexia acting up right there. So then that would be approximately 4.3%. Does everyone understand what I'm saying, right? So this probability tells us the probability that something might happen by chance, right? If our original assumption was correct. So it's all up to us, or kind of the situation, to say, like, how sure do you need to be that it didn't happen by chance, right? But you want to be fairly sure, right? So we typically say that that should be somewhere in the 10 to 1% level. You could think of, right, if it's something that's really out there, right? If you take something that's been accepted as true for thousands of years, maybe you would want a 0.01%, right? Something like that. So this is what we were hypothesizing it's less than. The two-tailed test is a little bit weirder in this, right? So here's our z. So this is the value that is based on our sample. But since, right, we're doing a two-tailed test. Hi. Oh, yep. All right. You cleared your calculator?
Yeah.
All right, great. All right, thank you. I will see you later. In this case, right, this is less than average, but you'd also want to find the probability that you might be that far off on the other end as well, right? So what's the probability that your value is as extreme? So when you do this two-tailed test, right, notice these both tails have the same area, right? So you want to find the area of one tail and then double it. Which tail is typically easier to find the area of? Well, your table finds area to the left. What does your table say on the top? Area to the left, right? You could find the area to the right of this, but then you would have to subtract it from 1, right? And then double it. Here you could just find, so you could do it either way, right? If right makes more sense to you, Frank, you can do that as long as you remember to subtract from 1, right? And my guess is you're going to, because you're going to know it's a small area, right? I'll even show you how to do it that way. So let's say left. All right, the number I was looking for was 0.163. That's here, right? Two is approximately 10.3%, right? Now, if you want to do it Frank's way and think, okay, I like the right one better, okay, then you look for the positive value in your z-table. Then you notice, right, you remember for significance level, right, you would then have to do 1 minus this, right, and then multiply by 2. That's fine, right? You probably wouldn't forget to do the 1 minus, right? That's another step. You probably wouldn't even forget to, because you notice this is a pretty big number, right? I'm typically looking for significance levels should be small numbers, typically. Right? So there's two ways to look at it, right? Each z corresponds to a particular p, right? So you can compare the z's to what they should be, or the p's to what they should be, right? If the z is more extreme than your critical value, right, on either the left or the right or both, if that's the type that we're looking at, then you reject your hypothesis, right? You fail to reject it if it's not as extreme as z is, right? Roughly speaking. The p-value method, which is the one that I'm going to teach you, because it's, for me, it's more intuitive, right? So I'm going to teach you the p-value method first. You just reject if the p-value is less than alpha, right? Your significance level. Because then you're saying, hey, I'm willing to accept, I'm willing to reject, right, my null hypothesis if I know that there's a less than 5% chance this happening if the null hypothesis is true, right? So if this only has a 3% chance of happening if your null hypothesis is true, that's less than 5%, so you would reject it. Final thing is writing things. This table is a little bit confusing, right? But the main thing, right, is if you reject, you want to say there's sufficient evidence to warrant or to reject, right? But that doesn't mean that you're sure, right? So you're like, I am saying there's sufficient evidence to warrant rejecting this hypothesis. It's not like 100% false, right? No statistical test can tell you something is true 100% of the time. Notice these two, right? When you do not reject the null hypothesis, you don't say that you accept the null hypothesis. You say you fail to reject it, right? There's not sufficient evidence to support your claim. And the reason why you say that is because our significance levels are typically small numbers, right? Even if you're like, hey, there's a 40% chance, right? It might be this high. Well, that's still more likelier than not, but that's not high enough for you to go against a claim that's from an authority, right? So it's not even to say that the evidence supports you not rejecting it, right? Just that the evidence is not strong enough to reject the null hypothesis, right? Think about it like a trial, right? You might even vote, right, in a trial, right? It's innocent until proven guilty, right? You might, right, if you're on a jury, you might vote innocent even if you think that the guy did it, if you're not sure enough, right? So you would, in that case, say the evidence provided by the prosecution does not warrant a conviction. You would not say the evidence provided warrants a declaration of innocence. You see what I'm saying, right? So that's the same thing here. You default, in that case, you default to innocent. In this case, you default to accepting the null hypothesis. So you never can say that your evidence supports keeping the null hypothesis. So for example, here, let's write down the null hypothesis so we can reject it, right? Null and alternative hypothesis. So the null hypothesis here, this is a proportion statement, right? So remember, the null hypothesis always begins with a what? So the null hypothesis is that P is equal to 0.27, right? And the alternative hypothesis is that less than, right? Because that's what you actually think. And we're talking about percentage of college graduates that smoke, right? So somehow we got significant evidence. We'll show how to do that later. Okay, so we rejected it. So that means we're supporting this, right? So, sorry, I'm just writing inconclusive for these, right? So if you don't, so we say it's not like completely conclusive, but you can say that the evidence actually warrants the rejection, right? So you would say that you can write in this way, right? There is sufficient evidence to write, you could write support the claim. You can write this in other ways, right? As long as it's not definitive, that less than 27% smoke, right? You would probably want to include more words. I don't want to jumble that up, right? So you might say college graduates that smoke, right? There's sufficient evidence to support the claim, right? Because we rejected the null hypothesis, right? If I did not reject the null hypothesis, right? We don't say accept, you say fail to reject. I would write there is not sufficient evidence to support the claim that less than 27% smoke. I would not write there is sufficient evidence to support the claim that 27% smoke, right? You write it as a double negative. Questions on this? All right, so finally, let's talk about type 1 and type 2 errors. So first thing to understand is neither error is a mistake. It doesn't mean something was done wrong by the experimenter, right? It was meaning that the evidence, right? It's like what we call a red herring. The evidence is pointing very strongly towards something that ended up not being true, right? And typically in statistics, you wouldn't know this. This is more of a theoretical stuff, so they try to minimize this, right? So a type 1 error, right, would be rejecting the null hypothesis, right, when the null hypothesis is actually true. So imagine going back to that coin flipping example, right? The null hypothesis for a coin is that the chance of getting a heads is the proportion of heads is 0.5, right? Right. So basically, the null hypothesis in that case is the coin is not rigged, right? Let's say I take the coin, I flip it 30 times, right? And 28 of those times it comes up heads. You would say, I think that coin is rigged, right? So you would reject the null hypothesis. But suppose it really was a fair coin and just something very unlikely happened when you did your experiment. You would be rejecting the null hypothesis, right? You'd be saying this coin is rigged, but you'd be wrong, right? So that would be an example of a type 1 error. Notice nothing wrong was done, right? You flipped it a bunch of times. You made the best guess based on the evidence you had in front of it. It just happened to be wrong, right? Luckily, we know the exact probability that this would happen, right? The probability of a type 1 error is always the significance level, right? Probability of a type 1 error is always the significance level, right? If you need to know, I want to know that there is if I get something that happens less than 1% of the time, right, I reject my claim. Well, in the 1% of the time that thing happens, I'd reject my claim, but I shouldn't have, because what can happen will happen 1% of the time, right? Well, then why not, right? Error is bad, so why not make alpha as small as possible? Well, when you make alpha smaller, right, the error probability of a type 2 error, which I'll tell you what that is, right? That increases, and we call that, the probability of a type 2 error, we use the Greek letter beta to represent. Calculating beta is more complicated, right? So we will not do this in this class. But just understand, right, if I decrease my probability of a type 1 error, I increase my probability of a type 2 error, right? So you want to kind of find the balance, right? So the type 2 error is not rejecting the null hypothesis when it's false, right? So you can see how that might happen, right? Okay. If I require, let's say I'm not going to check my null hypothesis, right? Unless the chance of this happening by chance is less than 1 in a million. Well, the chance of it happening by random chance is say 1 in 10,000. Still very unlikely, right? So I'm probably making a type 2 error there, right? I'm requiring, so think about making a type 2 error as requiring too much evidence to reject your claim, right? You have strong evidence, means your claim's probably false, right? The null hypothesis is probably false, but you're saying it's not strong enough by my standard, right? So most likely you're making a type 2 error there. So let's go back to our example. So remember our null hypothesis was that was the proportion, right? So let's go over it, right? So I told you a type 1 error, we do what? We do what when we should have done what? You reject when you shouldn't have, right? So in this case, right, you would be wrong, right? So if you reject the null hypothesis, then you confirm the alternative hypothesis. So in type 1, right, the type 1 error would be you conclude that less than 27% smoke when actually 27% smoke. Or you could say it more, but you typically say it this way. Right? This could happen, right? Say that you chose a sample randomly by chance, right? Where only 10% of the sample smoked. Let's say it's a big sample. You would say that's not likely to happen by chance. So I'm going to assume that my 27% was wrong. But it could happen by chance. And in those times it happened by chance, you would be making a type 1 error. Right? So a type 2 error would be concluding the opposite. 27% smoke when actually less than 27% do. Imagine this time, right, that the percentage that smoke is 25, right? That's the real percentage. So roughly 25% of your sample smokes. You're like, okay, it's less, but it's not less enough because my sample wasn't big enough to make that away, right? Make a bigger sample, you're less likely to make a type 2 error, right? This is more likely, but usually it's less catastrophic, right? Because, right, at least in terms of your reputation as someone who's publishing something, you don't want to publish something that is later turned out to be wrong, right? You don't want, so a type 2 error, right? You don't want to publish unless there's not something that's been confirmed many times. You're not going to typically, type 2 error study, no one reads it. Type 1, everyone does, and they want to prove you wrong, right? So that's one you want to be more careful about, right? Notice that the more evidence you require to reject the null hypothesis, the more likely you are to not reject the null hypothesis when you should have, right? So it is a trade-off of which most of the time, luckily, you won't have to decide what trade-off you want because I will tell you the significance level. But the person who designed the study decided what that trade-off was, right? You know, actually, I make fun of my wife. Actually, will say like, you know, in this situation, we'll talk about something that's happening in our life or in politics or something. She'll say this is an example where a type 1 error is catastrophic and type 2 error is okay or something. And I'll make fun of her because she talks like academic speak in everyday language, right? So, but typically, right, to actually know if a type 1 or type 2 error occurred, you would have to actually know the quantity that you're testing, right? So you typically don't know, right? If you're making a type 1 or type 2 error, you want to just think about what would be the consequences of making a type 1 error? What would be the consequences of making a type 2 error? What would be the probabilities of each of those things, right? That's what you want to do when you're making a study. But you'll never know whether you're making a type 1 or type 2 error, almost ever. Maybe in retrospect, right, with more evidence. Questions on the difference between type 1 and type 2 errors, because I know it's confusing. I'll make sure to get a lot of questions on the homework on that so you can get that down, right?